All right, hello everyone. This is the Arduino workshop session one, and my name is Sahas Foyekar. I'm a computer science major and the CS lead for UCR-UAS, and joining me today is Jeremy. Jeremy, would you like to also introduce yourself?
Yes. So I'm Jeremy Carlton. I'm the EE team lead at UCR-UAS. I was the instructor for session 0, which was last week. So this session is gonna hopefully build upon some of the concepts you saw previously, and then give you some interesting tools you can use with in your Arduino programs.
All right. Before we get started, we have some announcements we'd like to make. Trang, would you like to talk about UCR-US's announcements?
Yeah, so hi everyone. Just a reminder that all of these sessions will be recorded and the materials such as slides, the syllabus, and any other additional material will be posted onto our website at ucr-uas.weebly.com/workshops. You can find these links in the chat. I'll post them later. And we will have office hours right after this class with either Sahas or Jeremy. And if you don't want to miss anything, subscribe to our newsletter. We have at least more applications are open. If you're a current member and you want to gain more experience, then feel free to apply. And we will have our first ever aerospace conference. It's student led. We are spearheading that conference, and it will happen this Saturday at 11 a.m. So sign up on our website at ucrac.com. We'll see you there. Thank you, guys.
All right, thank you very much, Trang. And with that, let's go on to session one of today's Arduino workshop. So the very first thing that we want to talk about is state machines. State machines are really, really important for not only Arduino, but lots of embedded system concepts because state machines are essentially a behavioral model that allow us to that revolves around the use of using states at which different behaviors are set between each state and it allows the system to transition between one state to the other depending on different inputs that are detected by the hardware. So in this case, we have a model for a subway kind of turnstile where if before you can enter a subway, there is usually a rotating bar that you would need to enter a coin in or a card in to be able to turn the bar and enter the subway station. Otherwise, the door is locked. So the initial state is locked for this state machine. When you do if you try to push on the bar, since it's locked, nothing will happen. It'll cycle back into the lock state. And that's what the push transition is saying over here. However, if the system detects that we have entered a coin into the turnstile, we move from the lock state to an unlocked state, and this allows the user to pass through the bar. And pushing is another input that will be detected by the system that allow us to go from a unlocked state into a locked state. And then same thing as in the unlocked state, if you were to put another coin in, it'll typically give you back any extra coins that you gave into the machine and remain in the unlocked state until you actually gave the push input and go back into the locked state. So this is kind of a real world example of how state machines are worked, and they don't typically need to be associated with electronics. In this case, you can do all of this very mechanically, but it also is very similar to how it'll be working in writing state machines in Python, or not Python, my bad, in Arduino, which uses the C++ language. So how do we build state machines? State machines require a variable that'll keep track of what state we currently are in the machine so that we can kind of keep track of what stuff we need to do depending on what state we're at. And after this instructions of a state is executed, all of the inputs of the hardware are checked to whether, and we see whether or not we should stay within the same state or move on to another state. And over here, we have an example of how we can detect a input of a button to determine whether or not we light up an LED. So if the LED is detected to be on, we will, or if we are pushing on the button, we'll go into the on state of the LED and we'll turn the LED on. Otherwise, if we detect that the button isn't being pressed, then we will essentially say that we're going to an off state and we'll be turning the LED off. And to model this, I'll demonstrate off of a kind of a drawing. So how state machines will look for a button system is we'll have a state for on, and we'll also have a state for off, and we'll also have a hardware button if we are pressing on that button. So off will be our initialized state in it. And if we press on the button, that means we'll go from the on state to from the off state to an on state. So if button equals 1, we'll say 1 is on. We'll go from off to on. And then if it detects that the button, and if we are still holding on to the button, we'll cycle back into the on state. And then if we want to turn the LED off, we will let go of the button. So if we are no longer pressing on the button, that will allow us to basically get the input for B to be equal to 0, and we'll cycle back into the off state. And inside the off state, we'll constantly be cycling in if we are still detecting button press is 0. So this is kind of a very basic idea of how state machines are designed, and we'll be building on this in uh, future lessons of our workshop. So that is state machines. So the next thing we want to cover for this topic is a new type of hardware that we're going to be interacting with in Arduino, which is the potentiometer. A potentiometer is essentially a piece of hardware that allows the Arduino to take in an analog signal, which we'll cover in a bit, which ranges from a signal strength of 0 to 1024, 0 being the lowest possible input strength and 1024 being the highest. The signal produced by the potentiometer can be used for many different types of projects because of its ability to produce a wide range of signals. So unlike the input signal of a button, which is only capable of doing zeros and ones, we can use the potentiometer's mechanical hardware of turning a knob to adjust the input level. And an example of the potentiometers is produced, or the signal of a potentiometer is produced by spinning a dial, which will produce the range of our input signal. So how does the potentiometer work? A potentiometer will produce different strengths of signals by using a ranging resistance. So the lower the resistance, the higher the output. The higher the resistance, the lower the output. And you can kind of see in this model image over here, what's happening is we have three different pins for a potentiometer. We have ground, output, and VCC or power. So our powers will go into the green wire, and we'll cycle through the resistive strip to the ground, and output will be our knob. So depending on where our knob is, we will either increase the amount of resistance of the potentiometer or decrease it. And another way to view a potentiometer is it's kind of a varying resistor. So depending on where its position is on the wiper is on the resistive strip, we will have a different resisting ohms value. So what can we do with this piece of hardware? Potentiometers can be used in lots and lots of different kind of electronic devices. Some examples being being able to dim lights in your house. So if you turn the knob, it can increase or decrease the light intensity of light bulbs that are specifically designed for that. It can also be used for gaming joysticks. So depending on how much input you give to a joystick, it will produce a different kind of signal. So if you only push a little bit on this joystick, it'll make your character move just a little bit forward, and vice versa. If you press harder on it, it'll move faster. And it can also be used for controlling volumes on audio devices, or typically any kind of device that requires a range of different signals. So for audio, it can be like quiet to really loud. We'll also be using potentiometers. Anything that requires a varied input, we'll be using potentiometers. So using the potentiometer, we can, so when we're using the potentiometer for Arduino, we can use the input signal strength of the potentiometer to control the brightness of an LED using an Arduino board. So previously, we were only able to control an LED by setting its value to either high to be on, or its input or its output to be low for off. So kind of an but for an analog signal that is produced from a potentiometer, we'll be having a range from 0, or we'll be having 1024 representing on and 0 representing off. But any values between 1024 and 0 can be mapped to different intensities of a light of the LED. And because we're using an analog signal this time to control an LED when using the potentiometer, we now have all the values between 0 and 1024 to be able to adjust the brightness. So now we're going to move on to a demo in Tinkercad where we're going to be using the varying resistance of a potentiometer to be able to control the brightness of an LED. So so if you have the physical pieces of the Arduino in hand, you can use that. Or if not, we can be using the Tinkercad. Oh, we can use Tinkercad to kind of design it. So go on to tinkercad.com and you want to just go ahead and click on the circuits and create a new circuit. I already have a new an empty project built, and you'll be able to put all the pieces together in Tinkercad. So in order to build this particular lab, we'll be needing an Arduino board, breadboards, the potentiometer, a resistor, and an LED. So the first thing I'll drag in is my breadboard and my Arduino right there. And then I'll be also needing the potentiometer. So there's my potentiometer. I'll also need a resistor. Oops. I'll need a resistor right there and an LED. So now that I have all of my pieces, I can start to put it together. So first thing we need to do is wire up our power to our breadboard. So I'll connect ground to the, the negative, and I'll also connect, hold on, and I'll also connect my 5-volt power to positive, and that'll now give this entire strip power. So I can just use this strip in order to distribute power to all of the components that I'm going to be using. And I'll set up my potentiometer by placing it on the board, leaving the row A empty for any wiring. So I'll probably put it on row C or column C, and I'll wire up my potentiometer. So the first pin right here, terminal 1, will need to be connected to ground. So I'll have that connected. The third pin over here, or terminal 2 in this case, will be requiring power from and you can see this from the diagram. Ground and is the first pin, and power is the third pin. So I'll be hooking that up to power. And then the last pin is actually going to be the wiper. And the wiper is going to be giving us our output that we'll be using to control the varied resistance of our LED. So I'll actually be using a resistor to hook it up, and you would want to use the spin tool to spin it so that all of the bars on the resistor is on the right hand side. And I'll have it connected to the wiper, and I will start to hook it up to my LED. So I'll have it in parallel with the terminal 1 of my resistor with the cathode, and anode will connect back to power. And that's all we need in order to set up our potentiometer slash LED demo. So now when I start my simulation, you can see that the LED is lit up completely at the current state that our potentiometer is at. And if we were to spin it, you can start to see that it decreases in power depending on where the wiper is. So if it's all the way at 0, our LED is off. And if it's at the middle, it's kind of at a dim state, and you can kind of see it transitioning from a dim state to a bright state just by moving the wiper on our potentiometer. So this is the first way that we can use potentiometers to control the brightness of an LED. Are there any questions about this particular demo or how it works?
No.
All right. So let's move on to the next part of the session, which is how we can use code to control the brightness of our LED. So having a potentiometer by itself is very capable of being able to control an LED because of its varied resistance, but we can use code to get a more consistent output. And the reason being is because with analog signals, we can start to have kind of inconsistencies when it comes to pulling a signal from a potentiometer. We'll kind of go over that in future slides. So controlling LED states. So what we've learned about LEDs so far is that we can turn an LED on or off by writing to its particular pin that we assign it on an Arduino code. So if the pin is set to high, the LED will turn on, and if we set it to low, it'll turn off. And we saw that the varying resistance of a potentiometer can change the brightness of an LED. And this is because we're limiting the amount of power that is going to our LED based on the amount of resistance that our potentiometer creates. So, so far we can control an LED using code by having it either set to an on state or an off state. So what can we do to get a range of values instead of 1 and 0? So this moves into the idea of digital input versus analog input, or digital input output, analog input output. So what is digital input or output? Digital input or output can be either set to two different states, a 0 value or a 1 value, 0 being low, 1 being high. And they can only be used in two different states. There's only two different states that the input slash output can be at any given time. And this can be useful because it's extremely consistent most of the time, because since the inputs can only be 0 or 1, the, having data being lost through any kind of inconsistencies with the hardware is usually minimized because there's only two different states it can be at. And in order to use Arduino to represent digital input or digital output, we use digital read command and digital write command to express digital values. And some examples of our digital hardware are push buttons and switches that we saw. And we can see that from the push button, there's only two different states. Either you're holding down the button or you're not. And with switches, there's also typically two different states. With the flip switch in particular, either the switch is flipped on or the switch is flipped off. With analog input or output, we have a kind of different way of representing data. And it's instead a continuous input that can have a varied strength from 0 to 1024. And it's used when the input we need for controlling different hardware for our Arduino projects require a different range, as opposed to binary values that we get from digital input output. One of the problems with this could be that it's more volatile compared to digital input output, because since we have a range from 0 to 1024, it's kind of difficult to be able to keep it at a consistent value. And any small changes that occur with the hardware can change the overall output that we get from say a potentiometer, because let's say you had a potentiometer hooked up to setup, and that LED for our setup will only light up if the potentiometer is producing a value of 500. Well, if there's even the smallest nudge on the potentiometer, that'll move the signal strength maybe to 501, and that would no longer allow the LED to light up because we would only have it set to 500. So typically when we're working with analog inputs, we would want to give a range at which an action could occur. Otherwise, if we give it very, very consistent points, it'll be harder to be able to hit those states and be able to get the intended output for the overall process. And in order to do analog commands on the Arduino, we would use analog read and analog write to express these analog values. And some of the examples of analog devices are potentiometers, because you can use the turning mechanism on it to vary its strength. Touchscreens is also a really good example of a analog input. Typically, A good example for that would be with tablets like iPads, where if you are pressing your finger harder on the tablet during kind of a drawing app, you can produce a thicker and more full line. And if you were to kind of swipe really fast, really lightly across the screen without a lot of pressure, that produce a kind of lighter output, and that kind of represents analog really well. And another kind of good example would be a gas pedal. The more you press on the gas pedal, the faster the car will accelerate. The less you put on the gas pedal, the slower the car will be accelerating. So any questions about digital or analog input output?
No.
All right. So how can we use how can we use analog input output for our Arduino code, or how do we represent that for our LED? So this goes into another topic, which is what is PWM? So in order for input to kind of be a analog input to be properly represented for a lot of different hardwares on the Arduino, we need to be able to deliver power with something called pulse width modulation. It's a technique that is used for in hardware to be able to reduce the average power delivered to a system by separating the amount of times that the power is sent to any given electronic device into smaller packets per cycle. So you can kind of see in this graphic on the right that if we were to analog write 0, which means we don't want to give any power to our hardware, then we would have the cycles be set to 0 for each cycle. If we wanted a 25% power distributed to our hardware, we'd do analog write 64. And you can see in this example, for each cycle, only 25% of the cycle is at a 5 volt, then it drops back to 0 over and over again. And this averages out to only 25% of the 5 volts being distributed to any given hardware. And this can kind of scale to 50%, 75%, and at 100%, it essentially acts like a high signal or a 1. And for a digital input, where we just straight up give 5 volts to any given electronic. So kind of a recap, the longer the power is applied to a cycle, the more power delivered in average, which means um, in the case of an LED, the brighter it will be, or if you were to think about it for a motor, the faster a motor would spin. And small periods of power given per cycle will result in less power delivered in average. So in terms of hardware, LED would be dimmer, and for a motor, the motor would be spinning a bit slower. And PWM on an Arduino will be ranging from 0 to 255, and only certain pins on an Arduino are capable of delivering a pulse width modulation voltage. And in order to find which pins are capable of doing that, you'll need to find pins that have a tilde next to them. And we can take a look at our Arduino really quick, and you can see that some of our numbers like 11, 10, 6, 5, 3 are all have tildes next to them, and you can see that means that they are capable of doing PWM. So that's what the PWM tilde symbol means on your Arduino board. Any questions about pulse width modulation, PWM? All right, if not, we'll move on to the next topic, which is how can we use PWM to control the brightness of our LEDs. So we'll be doing a second demo for this, and this will be demo 2 out of 3. So make sure you don't close your Tinkercad after this example. And for this, we'll be using simple wires hooked up to an Arduino and using code to adjust the brightness of this particular um, circuit. So let me go ahead and remove some of the components that I already have. So I'll remove this potentiometer. Oh, I have to stop the code first. Remove the potentiometer. I'll be using the resistor. I'll just start rewiring from the beginning, however. So for this lab, we'll need a breadboard, an Arduino, an LED, and a resistor. So the first thing we'll need to do is we'll need to hook up our uh, positive and negative with power. So I'll first hook our ground to negative. And now, instead of hooking up power straight from the 5 volts, I'm actually going to use one of our PWM pins to control the power we actually distribute to the positive end of our board. So in order to do this, you'll need to pick one of the pins that have a tilde symbol next to it. In this case, I'll be using pin 11, and I'll hook this up to the positive end on our breadboard. So now our negative positive row or columns are being powered or will be powered with a PWM signal, so we can control the strength that is given to this into this column, and this will in turn allow us to adjust the brightness of our LED. So now to hook up our LED to the circuit, we'll just place our LED somewhere on the breadboard that's closest, preferably closer to our negative positive columns, and then hook up our resistor as to not burn our LED. And then we'll just need to hook everything else up to negative and positive. So I'll go ahead and do that right now. So on terminal 2 end, I'll hook up negative, and then on the anode side, I'll hook it up to positive. And that's everything we need in order to actually start creating our demo. Now all we need to do is write our code, because if we were to run this, it won't really do anything. So to write up this code, what we'll need to do is we'll go into our coding section and go into text code. And before we do anything, we actually want to initialize a pin that will be representing the LED pin that will control the brightness of our LED. So in order to do that, I'll be creating an integer variable called int LED pin. And what LED pin will represent? It'll represent the pin that will, the PWM pin that will allow us to control the brightness of our LED. In this case, I'm using pin 11, so I'll be setting integer LED pin to 11. Next, I have to set my pin mode to output so that I will be able to control the brightness of my LED using LED pin 11. So I'll replace 13 with the variable LED pin, and output is already set. So we are all good on the setup portion for this particular lab. All we have left to do is write inside of our void loop to determine what is going to be happening with our LED. So I'll delete all of this code and start fresh, and we'll actually be using, since we're working with analog signals this time, because we're working with the PWM, instead of using digital write, we'll write analog write, and we'll write to LED pin, and we'll set, initially we'll have it set to 0. So that means our PWM signal will be giving 0 volts to this negative positive column, and in turn that'll mean that our LED won't be powered up at all. So if I were to run this now, well, nothing will happen because we're still not distributing any power to the LED. So in order to get it to actually distribute power, first we will use the delay function so that we don't automatically switch between 0 to, say, 500 really, really rapidly, so that we can actually monitor it cycling between everything. So we'll be using the delay function, which any number you put inside of it will be the number of milliseconds we will pause before we execute the next piece of code. So since I want to wait for 1 second, I'll put 1000 milliseconds in delay. So after 1 second, then I want to power up my LED with a little bit more power. So I'll use analog write, and power up my LED pin and set it to 50. And then I'll end it with a delay of 1000. And what this will do is now I'll be able to see that my LED lights up just a little bit and pulses between a state of 50 and a state of 0. And if I wanted to give it to its max range, which is 255, I can just copy this code and have it transition a bit more. So I'll stop the simulation and add a bit more code. So I'll go from 50 to 100, 100 to, say, 200, and then end it with it hitting 255, which is the max. And now when I run the code, you'll be able to see that it's the LED now transitions between all of the different kind of brightness states, and then once it hits the end, it resets back to 0, and then begins that cycle again. And this is how we can essentially use uh, we can use PWM and code to control the brightness of our LED. Any questions about this particular lab?
No.
All right. So I'll go ahead and stop this and we'll head back into the slides and see what we have next to do. And the next thing we're going to actually do is our third and final demo for today, which is how can we combine the two elements of a potentiometer and a PWM signal to control the LED so that if we were to turn our LED or turn our potentiometer, we can use the signal that's outputted from the potentiometer, bring that into our Arduino, and change the state or the brightness of our LED. So that'll be the next kind of project that we'll be doing right now. Oh, that's it. We'll head back in here and I will disconnect all of the components and start fresh again. And for this, we'll be using the LED, the resistor. Let me turn the code off, and we'll need to get a potentiometer again. So now that we have all of our components, we'll start to hook everything up. So the first thing I'll hook up is my potentiometer to our Arduino to be able to extract a input signal from it. So I'll place it on row D or column D all the way at the bottom, and I will use some wires to get an input into my Arduino. So in order to get an analog in, I'll be using this set of pins on my Arduino that says analog in with A0, A1 all the way to A5. So in order to get my input, I'll first need to, before I get input, I want to power up my potentiometer. So I'll hook my potentiometer to positive and negative leads. So the terminal 2 is positive, so I'll bring it to the 5 volt. Let me scroll out a little bit. Oh, whoops, let me start it. Let me give myself a bit more room. So I'll be hooking up the, one sec. Um, okay, I see. So I'll actually be hooking up terminal 1 to power. So I'll do that first. And we'll be giving it 5 volts of power. And the terminal 2 will be hooked up to ground. So I'll bring that over to the ground pin. And the last thing is I'll be hooking up my wiper input to A0 so I can properly read what input I'm getting from the potentiometer. So go ahead and just get that right there. So now my potentiometer, not quite. I need to move it right there. All right. So now that my potentiometer is hooked up to my Arduino, I can start to get input from it. So let's actually go ahead and set that up first before we put in our LED and resistor into our circuit. So first, I'm going to go ahead and clear everything from my void loop. I'll clear everything from void setup, and I'll clear the very first variable, and I'll start from the top. So the very first thing I'm going to do is I'm going to initialize what my LED pin variable is going to be, or actually before I do variable LED pin, I'm going to actually initialize what my read val. I'm going to be initializing two different variables, a read val variable and a LED valve variable. And read valve will be reading input from my potentiometer to determine what I'll be setting my LED to. So I'll write that up, int read valve, and I'll set that to 0 to begin with. And then I'll also have my another variable that will be keeping track of what my LED value is going to be set to at the beginning. So that's going to be integer int LED val equals 0. And now that these variables are set up, I can actually start to kind of figure out what my input from the given potentiometer actually is. And to get that input, what I'll do is I'm actually going to use a new kind of command called a serial output, which is which kind of can be represented as how we would write to maybe a command line for programming in C++. And we'll go over that in the next few slides. But to set up our serial port, what we want to type in is we'll first type in a serial object dot begin, and begin is a function, and what we're going to pass into the begin function is something known as a baud rate, which will determine the number of bits that is going to be flowing from our potentiometer to our Arduino. And right now that might not mean anything to you, but don't worry, we'll get to that. So you want to set it to 9600 and then end it with a semicolon. So now we have our serial begin set up. And now what all we'll need to do to be able to get the input from our potentiometer is we'll need to first get input by using analog read. So we'll have read val equal to analog read, and we'll pass in the pin that we're reading from, which is A0. And now all we need to do to print out that value is we'll go ahead and do serial dot print ln. So we're going to print every time we input or every time we display a value in the serial monitor, we want to end it with a new line. So that's why we're doing print ln. And it's pretty reminiscent to anyone that might have done Java. That's kind of a similar syntax. And we'll put in read val into the serial println. So now if I were to start the simulation and open up the serial monitor, we can see that the value currently is set to 1023. And if I move the dial, we can see the numbers are starting to go down and all the way until I hit 0. And you can see that the range from 0 to, in this case, it's just 1023. So this is how we can see the input that our Arduino is getting from the serial monitor. So let me just go ahead and turn this off. And now that we know that we are getting our input, we will need to use our input to determine what our pin will be set to, which is pretty simple from here because it's kind of similar to the previous lab that we just did. So I'll just set up my LED on the other side of the breadboard with a resistor, and I will hook up a, a power and ground to my LED straight from ground and one of the pins that I'll choose. So I'll hook up ground onto this end, and then I'll hook up pin 10 because it has the tilde symbol to my resistor. And all we got to do now is hook this up using code and map my analog read value to the output value of my LED to be able to change the brightness. So I'll create a new value integer or variable integer LED pin, and that is set to 10. And then in my void setup, I'll set up my LED 10 to be an output. So pin mode LED pin will be set to output and semicolon. So now LED will be representing an output, and all we need to do is use a function called the map function, which will take a range from 0 to 1024 and map it to 0 to 255, because an output using PWM will only range from 0 to 255, and since our input is from 0 to 1023, we won't be able to use that full range, so we'll just kind of shrink it to fit the 0 to 255 scale. So after I print out my read val, I will have LED val set to the map of, I'm going to be mapping read val 0, comma 1024 to 0, comma 255. So just taking a look at our map function, all we really need, all of the inputs are, the first input is what input we're reading from, which is read val, And then this is what the input that we're going to be expecting from read val, arranged from 0 to 1024, and we're going to map that to 0 to 255. And once we get our LED val, all we need to do is use analog write and set my LED pin to the LED val. And if I were to run this, then we can see that moving the potentiometer will adjust the brightness of my LED. So when it's at 1024 or 1023 in this case, that's going to be mapped to 255, which is the brightest state of my LED. And then when I bring it all the way down to 0, then we can see that the LED is off because we mapped that to 0. And if I were to maybe map the 0 to maybe 100 instead, then we can see that the LED will never be technically in an off state because even at 0, the LED will still be off. Or even at 0, the LED will still be at a power distribution of 100. So that's how we can use potentiometer to control the state or the brightness of an LED. And that's kind of a culmination of everything we just covered. Any questions about this particular lab?
No.
All right. Well, so that's all the lab stuff for today. And now we're going to kind of cover what this serial monitor code is actually doing in the next few slides. So and for these next few slides, we won't be doing any more examples, so you can just relax and listen. So let's have an introduction to serial monitor. The Arduino board is good for controlling hardware, as we just saw. Controlling the LED is really easy to do with an Arduino board, but we can also use it to interface with different sensors and collect data, just like how you saw earlier. We were able to interface with the potentiometer and collect data off of it to see what kind of value that it's inputting. Since the board itself doesn't have a display, we won't be able to see this data for ourselves. However, we can connect the board to a computer. In this case, in our simulation, it's already connected because everything is done in software. But with an actual Arduino, you'd want to hook this up to your computer and you'll be able to see the display from the serial monitor. And the serial monitor simply just monitors whichever serial port that you're communicating with, the Arduino board, and allows you to see the data that is being transmitted over from the Arduino to your computer. So how does this work? The communication between a Arduino board and the computer is using a USB 2.0 protocol. So all the data that's communicated, all the data is communicated as bits, and specifically 8 bits or 1 byte is sent at a time. Incoming and outgoing data is also buffered. So if multiple bytes are sent before the first byte has been processed, so that the first byte before the first byte has been processed by the receiver, so it's essentially sending packets of information. And then the serial communication only works if both devices are sending bytes at the same rate. And this is known as the baud rate. So from our previous example, we set the baud rate to 960. And there's other baud rates that also communicate with different kinds of hardware. And when you're using Tinkercad, however, it'll already preset to whichever one that you are using or interfacing with. So that's just some things to keep in mind when you're trying to use the serial port to monitor what kind of input you're getting from any particular hardware. So the serial monitor is built into the, so if you're using the Arduino IDE, it's already built into that system as a box where you can kind of write messages to your Arduino board, and which is this kind of text box right here. And then it's also capable of sending and receiving messages into the message board. You can control the baud rate using this drop down. You can also control the auto scroll. So if you want to take a look at specific information, you can turn auto scroll off, have it run, and you can scroll through it yourself trying to find the information. And you can also set whether or not data is being sent from the monitor to the Arduino, whether it should terminate with a new line character. In this case, that'll be the setting right here. On Tinkercad, there's a bit there's isn't that as much functionality as the IDE, but we still have some stuff we can work with in the serial monitor, which is in this case it's just communicating with another program because everything is happening in software. So all the baud rates are already automatically detected, no setup is required, and there isn't any way for you to add a new line message. You'll have to do this yourself. In this case, we use the println function to accomplish that. So serial communication in programs. Before any serial communication can be done, the function serial.begin must be called in our setup. And one of the parameters for that is the baud rate that we pass into the parameter. So coming back to our example, in our setup, we have the serial.begin and we give the baud rate of 9600. And this will essentially prepare our program for serial communication at that specified baud rate by using the serial port object known as serial. And this object or this function will only be required once, so that's why we put it in setup. Now, there's two different functions we can use to get the input from our hardware, serial.print and serial.println. And they're able to send lots of different kinds of primitive data types, which include strings, integers, and floating points. So the only difference between print and println is that println will automatically print a new line at the very end. And when you have all the characters stored, and when you have a character stored as a byte, you'll need to send that byte as is using the serial.write instead. When reading incoming data on an Arduino program, you'll first need to verify that there is data to actually be read in. Then you'll read the data and typically store it in a location in memory. So serial.available will, with no parameters, will return the number of bytes that are available and will evaluate and when we are evaluating this particular function, it'll return true if there is data, otherwise false. And serial.read with no parameters will read the first byte that has not been read yet and returns it. And if the message is no longer than 1 byte, then serial.available will remain true and will call to serial.read to be able to interpret the next byte. And this actually brings us to the very end of today's particular workshop. So we were able to cover three major topics: state machines, uh, we were able to cover potentiometers and how we can interface that with controlling the brightness of an LED. And the final topic was serial monitors and monitoring how inputs are given. And so for this week's practice exercises, we can find that in the GitHub that Jeremy has set up for us. So all you need to do is click on the link and it'll take us to a GitHub repo, and all you need to do to access this week's exercise is go to session 1 exercises, and the README file contains the 2 exercises that um, we're going to be assigning this week. This exercise 1 is serial echo, exercise 2 serial adder. And this will be interfacing with all the serial knowledge that we have covered today. So that is actually all for this week. So yeah, any questions about what we just covered?
Can I just chime in really quickly?
Mhm.
These practice exercises, they're basically meant for you to like solidify your understanding of the topics we cover, and also to kind of explore beyond what we cover during the workshops themselves, and to help you like see that like if you're getting stuck on one of these exercises, in order to help you understand what you might be messing up on, we're going to be uploading uh, sample solutions to the GitHub repository, and those will appear in a folder called sample solutions in the same like space within the GitHub repository as you find the README, and those will just be Arduino sketches which can be opened up in the Arduino IDE, assuming you've downloaded that, or alternatively, you could probably open them in any other text editing software, and you can basically you'll be able to see code that was created by one of us to solve that exercise. And basically, there's no strict right or wrong answers to any of these. So if your code, and if the behavior produced by your code is matching the behavior produced by the sample solution, then you can assume that you were doing it properly.
All right. Thank you, Jeremy. And yeah, this will conclude our session one, and we'll be seeing you next week. And starting next week, we're going to go back to the regular schedule of meetings on Wednesdays. So we'll be picking up to that regular schedule. Um, so yeah, is there anything else that we want to kind of talk about before we close off today's session? Right. If not, then thank you everyone for coming to session one of our Arduino workshop, and we're excited to see where we can go from here. Starting from next week, we'll be covering more and more complicated topics and going over some more cool stuff that we can do with the Arduino kits that we are given on Tinkercad, as well as what you can get online.
Yeah, you'll be able to, I'll actually be introducing a mini project on in that session, and you'll be able to apply all of the almost all of the things you learned in this session, not everything except for the serial monitor, because it's going to be a project using LEDs. It's going to be like a light show. So you'll be able to experiment with how you can use PWM signals or state machines to make your light show more interesting if you choose to. But it's going to be an open-ended project, so you'll be able to bet and basically decide what pattern you create with your light show and then write the code necessary to make it happen. And I'll be basically spending most of next session talking about that.
All right, cool. So we got lots of cool stuff that we're going to be preparing. So hopefully you guys are excited, as much excited about it as we are.